Imagine a world so distant it remained a mere blur for decades, a tiny pinprick in the infinite abyss of space. This was our understanding of Pluto until 2015. When NASA's New Horizons probe finally soared past, it revealed a dwarf planet that was anything but monotonous. We saw towering mountains of water ice and a haunting, ghostly blue atmosphere. Yet, amidst this breathtaking beauty, scientists noticed something was terribly wrong. An icy anomaly was defying every law of physics we understood. Pluto's atmosphere was dozens of degrees colder than any scientific model had predicted. We are talking about a massive gap in temperature that no one could explain. How could a world 5 billion kilometers from the sun become even colder than the freezing void itself? What hidden force was chilling this dwarf planet to its very core for the better part of the 20th century? Pluto remained the ultimate question mark of our solar system. Floating more than 5 billion kilometers from the sun, it was little more than a flickering dot in the darkness. We knew it was tiny, about 2/3 the size of our moon, and we feared its thin atmosphere would simply freeze and vanish as it drifted further into the void. This concern made the New Horizons mission absolutely critical. It was a desperate race against time. Scientists knew that if they failed to launch by 2006, they might not reach Pluto before its atmosphere collapsed. Missing that narrow window meant losing our only chance to study this world for potentially hundreds of years. Against all odds, the probe departed in January 2006, beginning a 9-year trek through the frozen silence of space. When New Horizons finally reached its destination in July 2015, the data it sent back stunned the global community. Pluto was not a dead, frozen rock. It was alive with movement and activity. Towering mountains of pure water ice reached for the stars, while vast glaciers of nitrogen and methane flowed across the surface like slow-moving rivers. But the most incredible sight was just above the horizon, a fragile, layered atmosphere reaching over 300 kilometers into space. This delicate veil, composed mostly of nitrogen with hints of methane and carbon monoxide, glowed with dozens of distinct layers of haze. These layers scatter the distant sunlight, giving the dwarf planet a soft, sapphire blue brilliance that no one expected to see so far from home. How does this strange sapphire haze actually form? The process begins high in the atmosphere, with an unlikely ingredient, sunlight. Even though Pluto sits billions of kilometers away, where the light is 1,000 times weaker than on Earth, ultraviolet rays still reach its thin air. These rays carry enough energy to shatter methane molecules into fragments. Once broken, these pieces do not simply drift away. They react and bond together, forming complex hydrocarbons like ethane and acetylene. Eventually, they grow into solid, soot-like organic particles called tholins. As these particles drift downwards, they cluster to form the distinct layers of haze that scatter light and paint the Plutonian sky blue. Unlike the moisture-based mist on Earth, this is a chemical masterpiece born from the deep cold. Despite the visual splendor of the sapphire haze, scientists soon realized that something about Pluto's high atmosphere simply did not add up. Before the New Horizons probe ever reached its destination, planetary experts had spent years crafting sophisticated models to estimate the conditions of this distant world. Based on the known composition of the atmosphere, primarily nitrogen, with traces of methane and carbon monoxide, these models predicted a temperature of approximately 100 Kelvin. This translates to a staggering minus 173 degrees Celsius. It is a level of cold that is difficult to comprehend, yet for a planet sitting at the very edge of our solar system, it was exactly what everyone expected. However, when New Horizons finally made its direct measurements, the scientific community was sent into a state of total disbelief. The atmosphere of Pluto was not 100 Kelvin. It was significantly colder. The sensors revealed temperatures closer to 65 or 70 Kelvin. To the average person, a difference of 30 degrees might seem minor. But in the precise world of planetary science, this was a massive, inexplicable gap. It meant that the existing models were not just slightly off. They were fundamentally missing a major component of Pluto's climate system. Imagine the scene at NASA as the data trickled in. The atmosphere was behaving in a way that defied the standard laws of thermal physics as we knew them for such bodies. There was a hidden mechanism at work, an invisible hand reaching into the Plutonian sky and stripping away the heat far more efficiently than any gas alone could ever manage. The nitrogen, methane, and carbon monoxide were supposed to dictate the temperature, yet they were being overridden by something else. This discovery turned a routine flyby into one of the greatest atmospheric mysteries of the 21st century. Scientists began to scrutinize every detail of the environment, searching for the culprit behind this impossible chill. They compared the data against every known variable, refining their models and scratching their heads in frustration as the numbers refused to align. For several years, the discrepancy remained a haunting question mark in our understanding of the outer solar system. Was there a chemical reaction we had overlooked? Or was the very nature of Pluto's haze more influential than anyone had dared to imagine? The search for an answer would lead to a radical theory that challenged the very foundations of how we believe planets regulate their heat. Every calculation pointed to the same conclusion: the gases we thought were in control were merely spectators. Something else was dominating the climate of this small, icy world in me, radiating heat back into the void with a terrifying efficiency. The mystery of the 30-degree gap was no longer just a curiosity. It was a signal that our understanding of planetary atmospheres was incomplete. The scientific community was left in a state of bewilderment until 2017, when a planetary scientist named Zhang from the University of California, Santa Cruz, stepped forward with a theory so radical it felt almost like science fiction. He looked at the data from New Horizons and asked a question no one had considered. What if the haze was not just a passive, pretty feature of the sky? What if this sapphire veil was actively controlling the very temperature of the planet itself? Zhang's hypothesis suggested that these microscopic haze particles were acting as a giant planetary air conditioner. He proposed that the particles absorb the faint sunlight and then re-emit that energy back into the void, not as visible light, but as mid-infrared radiation in the incredibly thin air of Pluto. This process would be so powerful that it could cool the entire atmosphere far more efficiently than gases alone ever could. This was a revolutionary shift in our understanding of planetary science. For decades, we believed that atmospheric temperatures were governed almost entirely by gases. Think of the carbon dioxide that drives climate on Earth, or the methane that dictates the weather on Titan. The idea that solid particles could be the primary driver of a world's climate was strange, beautiful, and incredibly difficult for many to accept. But to prove Zhang was right, we needed a very specific type of evidence. We needed to detect a faint mid-infrared signal, a thermal glow, that could only be seen by a telescope with unprecedented sensitivity. Unfortunately, in 2017, no such tool existed. Earth-based telescopes were blinded by our own atmosphere, and even our best orbital observatories lacked the precision to isolate Pluto's tiny signal from the glare of its massive moon. Charon, Pluto is simply too small and too far away, a lonely speck orbiting in the deep freeze of the Kuiper Belt. The mystery remained locked away until a new era of exploration began in December 2021 with the launch of the James Webb Space Telescope. Equipped with a massive gold-plated mirror measuring 6.5 meters across, Webb was designed to peer into the coldest, most distant corners of our universe. It carried a specific piece of technology that would change everything: the mid-infrared instrument, or MIRI. This device was built to detect light in the range of 4.9 to 27 micrometers. This was exactly where the haze particles would emit their heat if Zhang's theory was correct. In May 2023, the moment of truth arrived. An international team of scientists pointed the James Webb Space Telescope toward the edge of the solar system. For the first time in history, we were able to see Pluto and Charon as two distinct worlds in the infrared spectrum. Every telescope before this had only seen a blurred-together mess of light, making it impossible to tell where the heat was coming from. But the powerful vision of Webb changed the game entirely, allowing researchers to isolate the thermal glow of Pluto's atmosphere with surgical precision. The momentous occasion finally arrived in May 2023. An international team of dedicated scientists who had spent years preparing for this very second finally pointed the James Webb Space Telescope toward the frozen frontier of our solar system. Their target was a world so small and so far away that it exists in a state of perpetual twilight. The tension in the mission control rooms was palpable. For the first time in the long and storied history of human space exploration, we were about to witness something that had previously been invisible to our most advanced instruments. The primary challenge had always been the relationship between Pluto and its largest moon, Charon. because they are locked in a tight orbital dance. They appear to most telescopes as a single, confused point of light. Every previous attempt to measure the heat of Pluto had been frustrated by this blurriness. It was impossible to discern which world was responsible for which thermal signature. It was as if we were trying to listen to a solo singer in the middle of a loud and crowded room. However, the James Webb Space Telescope, with its gargantuan 6.5-meter mirror and state-of-the-art infrared sensors, changed everything. It possessed the unique ability to finally separate these two celestial bodies in the mid-infrared spectrum, allowing us to see each world as a distinct and individual entity for the very first time. This was a monumental technical breakthrough. By isolating the light of Pluto from the light of Charon, researchers could finally focus their attention solely on the dwarf planet's atmosphere. As the data began to transmit across the vast distance of space, the team noticed a phenomenon that was truly breathtaking. The thermal glow emanating from Pluto was significantly more intense than what its icy, frozen surface could ever produce on its own. This infrared brightness was the definitive evidence scientists had been searching for. It proved that there was a source of radiation located high above the ground, hovering in the thin air. The scientists were witnessing the cooling mechanism in real time. The observations confirmed that the atmosphere was not just a cold blanket, but an active radiator. When they compared these new, high-resolution measurements with the theoretical climate models developed back in 2017, the results were nothing short of miraculous. The data points from the telescope fell onto the predicted lines with a level of accuracy that is rarely seen in planetary science. This near-perfect fit confirmed the radical theory beyond any reasonable doubt: the Sapphire Haze of Pluto is not a passive bystander. It is a massive, planetary-scale engine of cooling, actively glowing in the infrared spectrum as it pumps heat out into the universe. What began as a daring and speculative hypothesis by a few brave researchers had now become a cornerstone of our scientific knowledge, backed by the most precise evidence ever collected by mankind. The mystery of the 30-degree temperature gap was no longer a mystery. We had found the silent driver of Pluto's climate, hidden in plain sight within the sapphire layers of its sky. This revelation did not just tell us about one small world. It proved that our understanding of how planets manage their heat was far more complex than we had ever imagined. The resolution of the mystery surrounding the Sapphire Haze of Pluto is far more than just a victory for planetary scientists. It represents a fundamental shift in how we understand the very nature of worlds across the cosmos. For the longest time, our understanding of weather and climate was built upon the foundations of our own home, on planets like Earth, Mars, and even the hellish landscape of Venus. It is the atmospheric gases that perform the heavy lifting. These gases, whether they are nitrogen, oxygen, or the carbon dioxide that drives our own greenhouse effect, are the primary actors in the thermal drama of a planet. They are the ones that absorb the warmth of the sun, trap heat near the surface, and ultimately dictate whether a world is a garden or a wasteland. In these traditional models, small solid particles such as dust, soot, or volcanic ash were always considered secondary. We viewed them as minor contributors, perhaps capable of reflecting a bit of sunlight or causing a temporary cooling after a massive eruption. But they were never seen as the masters of the system. Pluto has completely overturned this long-held assumption. For the first time in the history of space exploration, we have discovered a world where the haze, and not the gases, is firmly in the driver's seat. By discovering that these organic particles are the primary reason for Pluto's extreme chill, we have been forced to rewrite the rulebook of planetary science. This revelation carries profound implications that stretch far beyond the cold reaches of our own solar system. As we peer through our telescopes at the thousands of exoplanets orbiting distant stars, we are beginning to realize that many of them may not follow the rules we once thought were universal. There are countless worlds out there, particularly those that orbit far from their parent stars, or those shrouded in thick, mysterious atmospheres that might be governed by this same haze-driven logic. If we continue to apply our old gas-based models to these distant Earths and super-Earths, we risk fundamentally misunderstanding their climates, their chemistry, and even their potential to host life. Pluto has taught us that the universe is far more creative and diverse than our early theories allowed. What began as a simple investigation into why a tiny, distant world was 30 degrees colder than expected has blossomed into a story of cosmic significance. It is a reminder that in the vastness of space, even the smallest anomaly can lead to a breakthrough that reshapes our entire perspective on the universe. We have learned that the origins of life and the habitability of worlds are tied to complex chemical dances that we are only just beginning to comprehend. As we look back at the images captured by New Horizons and the precise data provided by the James Webb Space Telescope, we see a Pluto that is no longer just a lonely outpost at the edge of the dark. Instead, it is a vibrant, active laboratory that has given us the keys to understanding a new class of planetary climates. It is a testament to human curiosity and our relentless drive to uncover the truth. No matter how many billions of kilometers we must travel to find it, if you have found yourself as captivated as we have by this extraordinary journey through the deep freeze of space, we invite you to join our community of cosmic explorers. Please leave a like on this video and subscribe to our channel so you never miss an update on the latest discoveries from the final frontier. Share this story with your friends and family so that more people can marvel at the hidden secrets of our universe. If you have your own theories about the Sapphire Haze or questions about what lies beyond the Kuiper Belt, please leave them in the comments below. We would love to hear your thoughts and continue this conversation as we unravel the mysteries of the stars together. Until next time, keep looking up.